Someone's inviting me to give a talk. It wasn't me, I swear to God. Ask that, they definitely. So I just thought I would, it was hard to know what to talk about because I was sort of, I thought I would try to transmit the reason I love this topic. I was going to call this Why I Love Service Bundles. And it's just because it involves so many parts of mathematics. So let me start out. Sorry, I cheated here. Service bundles, one of the quick things when I say like why study service bundles, particularly why group that as a topic of mathematics, just very, very quickly, it's in topology, it's sort of the simplest, you have theory of vector bundles, this rich theory, and this is really the simplest nonlinear bundle theory. Nonlinear just, it's the diff, the structure group is diff of the surface. Of course, there's diff of the circle, which is extremely rich, but in some sense, just within our understanding and just as outside of our understanding. In three-manifold theory, it was the first way to construct lots of examples, of course, and we'll do that. And that's the other thing. Thanks to the organizers for asking me to speak, for pushing me to speak, but I should have given the first talk, because my talk is going to be sort of the introduction. Sorry, I'm not going to change, but yeah. So anyway, for three-manifold, we now know that basically almost every three-manifold, except for a few very specific examples, is finally covered by a surface bundle, by work of lots of people, including Hegel. In four-manifold theory, we heard from Dieter, I don't really need to say much more, it provides lots of sort of a third of the known examples of aspherical four manifolds, lots of examples of symplectic manifolds and algebraic manifolds. In geometry, when you study the theory of bundles, it's not that hard to prove that if you have any surface bundle over any base, and the fiber has a metric of non-positive curvature, okay, and you're not like there are no local torus factors, so you're not like taking a product with a torus, then either you're finally covered by just a product, so there's not really a theory, or your fiber's a surface. So that's pretty compelling to me that like surfaces are special, they have the most automorphisms. This is when the fiber's dimension bigger than 1. Finally, in algebraic geometry, why are surface bundles so ubiquitous? Why are algebraic geometers obsessed with MG? There are lots of reasons, but one of them is that for any smooth, irreducible, quasi-projective variety, if you give me any point, there's a neighborhood of that point, a Zariski open neighborhood, that fibers, that's a family of curves over a quasi-projective base of dimension 1 less. So these are ubiquitous, every variety is made up of these things. Okay, that's all I wanted to say for that kind of stuff. Now let's do some mathematics. Okay, let me just start out with some examples. Yeah, I'm not, okay, examples of surface bundles. Well, one of the easiest ways to construct is what are called flat bundles. Flat is equivalent to admitting a flat connection, but we'll take this as the definition of flat. If you're given a homomorphism from the fundamental group of a space into diff plus of sigma g, you get a corresponding bundle. I'll call it E sub rho. You define it to be the set of pairs z comma w. Sorry, so what you do, you take, let me say it this way, you take the universal cover, you just do the Borel construction. You take the universal cover across the surface, and you mod out by the equivalence relation z comma w is equivalent to, well, pi 1 of the base acts, you just mod out by the diagonal action of pi 1 of b on this product. You act by deck transformations, and that action is free, g dot z, and then you act on the fiber by the representation. Okay, and because the action is free, and there's a natural map from that projection onto the first factor, that's just the covering map, but then the fiber is sigma g. Why can't points be identified on 2 different fibers? It's because the group, that fundamental group is acting freely on the universal cover. So you never identify 2 points in the same fiber. These are called flat bundles, and they have many remarkable properties. So, okay, for our definition, this is the definition of flat bundle, something coming from this obstruction. One thing I'll just note that you can record here, there's a homomorphism from diff of the surface to pi naught of diff. Everything in sight is orientable, the bundle's orientable, I'm ignoring it. And this is what's called the mapping class group, as I think everybody knows. And this representation is called the monodromy representation. It records how the fiber is changing as you move around loops in the base.
In this construction, you can also see the flat connection.
That's right. You can see the flat connection. There's a foliation that are covers of B. There's a transverse foliation, each leaf transverse to each leaf in the fiber. Okay. Another place that surface bundles come up naturally are in algebraic families of curves. And I thought I would just write one down, sort of a very classical one. Let me fix D greater than or equal to, let's say 2, then N greater than or equal to 2, greater than or equal to 3. So I'm going to do the following. Look at H of D comma N, define this to be the set of X comma Y, such that Y to the D is equal to X minus lambda 1, X minus lambda N, where the lambda i's are complex numbers, all distinct. So sometimes this is called the moduli space of such a thing is called a D superelliptic curve. When D is 2, it's hyperelliptic. These are the hyperelliptic curves. I guess this is the affine version. You can, if you do the projectivization, you get a projective curve. So topologically, this is a surface of a fixed genus, which you can get from the degree genus formula, but it might have some punctures. And I guess what I want to say is, here's a nice way to think about it. You take the complex plane, let me draw it as the Riemann sphere, because there's the point at infinity, and you take the set of, this is n tuples, it's unordered configurations of n points in the complex plane. Right? You're recording the roots of the polynomial. You can think of this as a polynomial just P of X, a degree n polynomial. So this is the space of monic degree n square-free polynomials, so distinct roots. That's it. Okay? And that's the same as unordered configurations of points. And you're fixing a D. And so what you do is, for a given configuration of points, what does this surface look like? Well, you're taking a D-fold branch cover over all of these. So you remove all these points, you map to, you get a free group, right? Pi1 is a free group. You map each generator, which is representing around each one of these things, to, you map the whole thing to Z mod DZ, and you map each generator to the generator in Z mod D. And you take the branch cover. And then infinity, you have to do what you have to do to make this work. Okay? And so there's this beautiful bundle. This thing fibers over the space of monic square-free polynomials. And the fiber is this fixed genus thing. Okay? There's a very beautiful paper by Kurt McMullen that is a nice sort of history and study of this bundle. I mean, it's much older than McMullen, but it's called Braid Groups and Hodge Theory. But it's like just a good source. For sort of background of this. Okay, but that's an algebraic family. I mean, there's very specific families you can write down. Okay. And maybe I'll give one more. Again, I'm sort of doing this for I want to do the lowest common denominator so that we all have a common thing. And so I know everybody's been mentioning each of these things. But the third thing, which is also algebraic, is the Atiyah Kadar example. Yeah, I apologize to Atiyah. He did do it independently. It was explained to me. I was confusing two papers. So I'm sorry. Okay, so let me just very briefly give you the construction. I know there's a very simple way to talk about this in terms of branch covers, but let me show you. So this is a four-manifold, and it's going to have the property that G and H are going to be equal to 2, and it's going to be a holomorphic fibration. Now, that's bad to say holomorphic fibration. It's called a Kodaira fibration. It just means the map pi is holomorphic and the map is regular, so it's a fiber bundle topologically. But see, it's not locally trivial holomorphically. The key point is that the complex structure on this is changing. And how you do it, here's a nice way that it was first explained to me, you take a surface of genus G, you can do one of genus 2, and you take an involution tau. If you want, just take a surface and take a twofold cover. Then you get a new surface with an involution tau. And so what do you have to do to build a surface bundle? Well, you give me a point, x, and I have to come up with a genus G surface. Now I want to do this in a way that is varying algebraically with x. Now you see, that bundle up there, it's clear. You see, as I move the points around, you're getting a different complex structure. Think of it this way. I should have said this up here. If you have the moduli space of 3 points, right? Any 3 points are equivalent to any other 3 points on the sphere by a projective transformation. So there's only one complex structure on the sphere minus 3 points. Right? Up to, right? But when you take 4 points, what's the moduli space? What does this moduli space look like when n is 4? Well, up to the action of PGL 2, you can take 3 of the points to 0, 1, and infinity. I'm ignoring ordering versus unordered. 0, 1, infinity, and that 4th point moves around. Right? And you get different complex structures. Now what you show is, if my 4th point is here, and I take the default branch cover, and your 4th point is over there, and you take the default branch cover, those things are not biholomorphic. That's an exercise. Okay? It's clear that downstairs are not biholomorphic. Okay? So that's why the complex structure is changing. And then when the points come back, the surface comes back, but of course there's a monodromy. It doesn't come back to itself via the identity. So this example, how do you vary something algebraically? There, it's clear. The lambdas are varying algebraically, and so the surfaces are varying algebraically. I wrote the equations. What you do here is you take x, then there's a canonical point attached to x. I'm thinking of like this, hyperelliptic involution. But there's an involution, so given any x, you get a tau of x. And now what I'm going to do is I'm going to take the homology cover. If this surface is x, I'll call this x twiddle. The homology cover. Let's just take the Z2 homology cover. Okay? And then what I'm going to do is I'm going to take let y sub x. The homology cover is just the one where the kernel, you have a map from pi1 of x onto h1 of x with z2 coefficients. Z mod 2.
Oh, okay.
So it's a finite sheeted cover, and I'm going to let y sub x be, I'm going to take x, I have to do something non-trivial to change the complex structure. I'll take this finite cover, and then I will take the twofold, 2 is not special, but twofold branch cover of x twiddle over P inverse of the set x tau x. There's a reason why you're doing all of these steps. You want, but let me not, this is just, I'm going to give you the flavor of how you construct it. And then that's y sub x, and then the Atiyah-Kadira example is the bundle of y where the fiber over x is y sub x. Y sub little x. Okay? And you can see it's varying algebraically, and we did something non-trivial. And you have to prove that the complex structures are changing. Anyway, those are the examples.
Do you need a fixed point free involution?
Oh yeah, fixed point free involution, thank you.
So not the hyperelliptic.
Fixed, not the hyperelliptic, point free. So it's exactly not the hyperelliptic. Yeah, thank you.
And you can't do it in genus 2.
You definitely can't do it with genus 2 fiber. Yeah, I don't think you do it with genus 2 base either. It is impertinent, even for somebody who's a former student. To ever correct your advisor. Even if you're a former student. Yeah, I'm kidding. Okay, so any questions? I want to move on. I want to talk briefly about the monodromy representation. I'm aware I'm giving a basic talk, but that's what I'm going to give. So we're all on the same page. Okay, so I just wanted to say, any surface bundle determines a monodromy representation there's many ways to define it. And of course, as you know, what's happening is that it's this to the mapping class group of sigma g. And of course, what you do is, given a loop gamma in the base, your fiber, what does it mean to be a surface bundle? It means you're locally trivial, you're locally a product. Right? So I give a path in the base. I'm supposed to give you a homeomorphism well-defined up the homotopy of the fiber. Well, what I do, I cover the path with little charts where my bundle is a product. In a product, there's a canonical identification of any two fibers. So identify, 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 and I come back to where I started and I get a homeomorphism. That's not well-defined. It would change when you change gamma up to homotopy, but it's well-defined up to homotopy. And that's what the monodromy representation is. Okay? Now there's an algebraic view that this short exact sequence gives you a long exact sequence in homotopy. 1 goes to minus sigma g. When g is, let me just say g is at least 2. Because what happens, the long exact sequence in homotopy, you'll remember that the image of pi 2 of the base in pi 1 of the fiber is abelian. And so pi 1 of sigma g has no,
It lands
sorry.
in the center.
No, I don't want to do that. It's in the center. And when you have no center, so you get this. But anyway, whenever you have an exact sequence of groups, you get a representation from the quotient group to the outer automorphism group of the kernel group. How? I mean, this is true for any three groups. A goes to B goes to C. Why? You give me an element down here, little b, I pick any lift, b twiddle, and then I take conjugation by b twiddle, acts as an automorphism here, right? It's a normal subgroup. However, you chose a lift. I could choose a different lift, and my choice of lift might be b twiddle times something here. And I get conjugations, a different conjugation. But it's well-defined up to conjugation by elements in here, so that's why you get an outer automorphism. Okay? Now there's a map from the mapping class group of a surface to the outer automorphism group by just sending f goes to its action on the fundamental group. Now it moves a base point, so it's only by outer automorphisms. And this isn't isomorphism. This is called the Dane-Nielsen-Baer theorem. It's really basically due to Dane. The other guys contributed like the technical, crucial, but technical guys. What I love about this is that it connects two parts of math. This is purely algebraic. I give you a group presentation. What are the outer automorphisms? This is purely topological. It's diffeomorphism group. Dane's proof is via hyperbolic geometry.
Isn't there an orientation issue with them?
Oh, sorry, yeah. I'm going to call it out, mod plus or minus. You have to throw in the orientation reversing. Yeah, you can do, yeah. So it's not quite the mapping class group, so it's extended one, or maybe I should call it, yeah, so there's an orientation issue, which we're going to ignore. Okay, so, questions? Okay, so monodromy, I think it's safe to say is the most important invariant of a surface bundle because of the following sort of remarkable theorem. And this is like Earl and Niels in 1969, and then Shax came in for the punctured case, which is important. But let G be greater than or equal to 2. It's very interesting in the other cases, as we heard before, in Johannes' talk. Then there exists a bijection. Yeah, and I'll prove this theorem. Sorry, I'll use the Earl's theorem. They didn't exactly prove this, they proved the main step in this. Between the surface bundles over a fixed base up to bundle isomorphism. So it's like a fibrillized diffeomorphism where it covers the identity. I claim there's a bijective, and I want between that and just homomorphisms, conjugacy classes of representations of pi 1 of the base into the mapping class group up to conjugacy. So if you have a representation of the mapping class group, I can compose it by just conjugating everything by a fixed mapping class. That's what the action is. So you see that the classification of bundles exact in genus at least 2 is exactly equivalent to understanding homomorphisms. So that's where the mapping class group comes in. And I just want to prove it. Again, I'm sort of repeating stuff that Johannes said beautifully, but I figure I may as well butcher it. Yeah, so the left, so, okay, so the left-hand side there, the left-hand side, bundles up to isomorphism, one of the useful things, it's just, you can always construct a classifying space for bundles, where bundle isomorphism, and here you just call it B diff of whatever the fiber is. Here it's orientation preserving. It's homotopy classes into the universal space. I mean, I think, was that Renee Tom's idea, to build a universal space that classifies everything? And then,
I think it was Milner.
oh, that was Milner before?
The idea was probably the other form, maybe.
Yeah, I mean, it seems amazing. But it's a great idea, but then I claim that the homotopy classes of B into this crazy, B diff is some crazy space that has a homotopy type of an infinite. So any model has to have a homotopy type of an infinite serial complex. But I claim this is homotopy classes of B into B mapping class group. Now when you have a discrete group, this is, and I'll say why, I'll say since, and this is Earl's theorem for genus greater than or equal to 2, because diff naught of sigma g, diffeomorphisms, homotopy identity, isotopic identity, same thing, is contractible. It's homotopy equivalent to a point. And therefore, diff plus of sigma g is homotopy equivalent to pi naught. Right? The picture is diff has all these components. It's topological groups, so they're all homeomorphic to each other. And I'm telling you that each component is contractible. So pi naught of diff, sigma g. And therefore, their classifying spaces are homotopy equivalent. And therefore, this is true. This is otherwise known, this next equality is notational. When you have a discrete group, it's a k pi 1 space. So it's a k mapping class group 1 space. And just by k pi 1 theory, this is pi 1 of p to the mapping class group. Up to free homotopy, and the free homotopy comes in by just blotting out by the conjugation action. Okay, so that's the proof of that theorem. And I would just like to point out, this is my thing, sorry for my students who've heard this like 50 times. This theorem is really a miracle, and I would like to point out why the theorem is an absolute miracle. You see, here's this flat bundle. We all can build, if I give you a bunch of homeomorphisms, you can just like build the thing, build the surface bundle. But I'm here with this monodromy representation. I didn't give you homeomorphisms. Like take the generators of pi 1 of b, and each one of them, I give you a mapping class, that's the homeomorphism up to homotopy. How do you build a manifold by gluing things up to homotopy? They're not going to be well defined. You can't do it. I don't know how to do it. And in fact, you sort of can't do it in a simple way. But by the way, this theorem says it exists. I can just specify any monodromy and a bundle exists. So I would say I'd love to see a concrete construction or a proof that it's sort of an algorithmically unsolvable problem. Does anybody have a guess? I would sort of guess that it's actually algorithmically unsolvable. Just because I can't do it. But you see, and you might say, well, maybe it's the case that every bundle is flat. And the thing is, that's not true. See, if every bundle happened to be flat, then they'd all come from the construction. And there's a beautiful theorem of Morita from maybe the 1980s that says, I don't want to remember and list all the names. I'm just going to put g greater than or equal to 6. 6 to the 6 to the 10 to the 10 to the, no, it's like 6 or 8 or something. Let g be greater than 6. Then there exists non-flat bundles over 6-dimensional manifolds I'll say why 6-dimensional. So here's an 8-dimensional manifold fibering over a closed, aspherical, in fact, 6-dimensional manifold. And by non-flat, I mean, i.e., you can look at the monodromy representation, pi 1 of b, to the mapping class group. Flatness is exactly, by our definition today, it's coming from diffeomorphisms, and you cannot do it. How do you prove you can't do something in topology? That's what algebraic topology is designed for. And I'll just say it uses, once I say this, so it uses bot vanishing plus the third Morita-Mumford class is non-trivial. So you're actually, the MMM classes are actually used for something. I mean, I knew you knew that, but I mean.
So I think I need G at least 9.
Yes, okay, thank you.
Within known stability range.
Yes, you need E3 to not be 0. Okay? And in fact, let me just state an open problem that I've been advertising for a while, that I personally think is a fundamental problem if you think flat connections are of any interest whatsoever, and you want to understand them. I mean, I think it's important to find problems that are sort of not infinitely hard, but probably within reach, but some new ideas needed, so, So, does there exist? I mean, I conjecture yes, and I even conjecture the Etiokadara example is the example. Does there exist a non-flat surface bundle over a surface? It's a very fun problem to try. Well, it's fun for a while until you realize you have no understanding whatsoever the actual depth of the map, and then it's sort of embarrassing. But
Benson, is
yes.
it somehow obvious, or can one see it, that this Etiokadara example has a flat connection?
No.
Obvious?
Oh yeah, you can prove it does not. It can't have a flat connection. But saying does there exist a flat connection is what you're asking with that. So given sort of kind of geometric structure, you want to ask if you give me a connection, I can compute the curvature. Just by the way, for people, I guess I don't want to get too much into this. We can talk after. But I'll just say, why do they call it flat? They call it flat. What does that have to do with like lifting the diff? It's really just saying you have a flat connection. You just take a horizontal fold. You pick a connection. What does it mean to be flat? Well, you define as you know, you define the curvature of a connection in terms of the form. You get you have a two-plane field. That's the kernel. It's given by a two-form. And you want to know, is that integrable? That would give you a transverse foliation, and that will allow you to lift this thing. Well, you write down the Frobenius integrability theorem, the version for forms, which, and you call that curvature. So when that's 0, you get integrable. So that's what. Okay. So, okay, I'm going to move on to. I want to talk about. My goal is basically maybe to talk about two main things, I should say. I wanted to do the basics, and to clarify too the relation to
Can I ask you a question?
MG, because all these things have been flying around in talks and just for people, yeah.
So, how is this related to this thing that there are subgroups of the mathematical group that are not realized by diffeomorphisms?
It's the same thing.
No, it's the same thing, exactly.
So it exists.
No. It's not known for
Over surface.
Yes.
over surfaces.
But how
That's
about,
what I was saying. He did it over a 6-manifold. There's also, you could ask over a 5-manifold or 4-manifold or 3-manifold. That would be really interesting. Yeah. So there's no groups that are known to not live.
yeah.
Spesfina Church, and I should do a shout out to a student. Spesfina Church, Suto, did sort of, there's a version with section, and they showed there are surfaces that you can't, but it's sort of, yeah, we can talk after. Okay, I just want to give the relation to MG. Now, MG, it's the moduli space of Riemann surfaces. It's all the, if you want, it's like the genus G, smooth, algebraic curves, up to isomorphism. It's also the set of conformal classes of metrics, of Riemannian metrics, on a given smooth surface. It's also the space of hyperbolic metrics on a surface up to diff naught, as we saw, I think, in Johannes' talk. It's also the complex 1 manifolds. It's not each of the complex 1 manifolds homeomorphic to sigma g up to biholomorphism. I can give 5 more descriptions. So this is why I think MG is like, one of the fundamental objects of mathematics. It's because these are all completely different categories, and yet they're all reflected in this one object, and they all must be connected because they're all encoded by this one object. And as people know who study MG, like a lot of the field is basically connect the thing that looks easy here to a thing that looks easy here, but you can't get them easy in the same frame of reference. And it's somehow I think it's because uniformization theorem is non-effective. And if it was effective, none of us would be here. We'd have all problems solved for this thing. But anyway, whatever. Okay? So the relationship with the mapping class group, let me just say this. Using complex analysis, you get, there's the Teichmuller space, which I know people have heard of, and this is a bounded domain. In fact, it's homeomorphic to a 16 minus 6, r to the 16 minus 6, but it's a bounded domain. It's a complex manifold, and the mapping class group acts on it properly, discontinuously, and freely. These are non-trivial and beautiful theorems. Good reference is the book by Farb Margalit, Primer in mapping class groups. Uses the light spectrum, hyperbolic geometry. Anyway, and so the quotient, there's always this problem. It's not a manifold because, oh, sorry, not freely, sorry. And not freely. And the quotient is mg. I think this was mentioned by Edward. There's a torsion-free subgroup of finite index. If you look at, I'll call it mg of 3, and I'll just define mg of 3 to be, you look at all the mapping classes that act trivially on the first homology of the surface with Z3 coefficients, for example. 3 can be replaced by any number bigger than 3. This thing is a manifold. Why? Because this mapping class group is torsion-free, and stabilizers of points are finite, and so it acts freely. So this is an actual manifold, and it's contractible universal cover. So this means that this finite cover of moduli space of Riemann surfaces is a k-pi1 space. So it's a k mapping class group 1 space. Right? So whenever I say the cohomology of a group, I mean the cohomology of a k-pi1. Right? A k gamma 1. Cohomology of gamma is the cohomology of k gamma 1. And this is a model. It's a nice finite dimensional model. Very rare for groups to have a finite dimensional model for their k-pi1 space. But then this implies there's like an easy transfer argument. That's like in our book, for example, super classical. This means, so there's two, you have a finite sheeted cover where like the homology of this group, this torsion-free group, by definition, is the homology of this space because it's a k-pi1 for the group. The integral homology, any coefficients you want. Now this is happening in a finite cover. So there's a transfer, which is an averaging argument. You need Q coefficients. So with Q coefficients, you get that the cohomology algebra of Mg is isomorphic to the cohomology algebra of the mapping class group. This is why sometimes it's called a rational classifying space. I think Edward called it, I forget what he called it. Something classifying space. Virtual classifying space. Okay, so questions? So sometimes I'll write cohomology of Mg, cohomology of the mapping class group, cohomology of B diff, it's cohomology of B diff. Okay? Okay, questions? So it's bringing in algebraic geometry. By the way, there's lots of other deep connections to 3 manifolds that I didn't even mention that don't come from surface bundles at all. They were, I think, alluded to last night at 8:27, or wherever pitch came, so 8:42. Anyway, okay, so Questions? Okay, so that's the relation. Maybe I'll title this sort of, this is something again for graduate students, although I've talked to people who are, I've talked to well-known professors who study X, and then you ask them, why are you studying X? And, I'm having fun. So that's fine.
Because it's there.
Because it's there, but they have no idea about, like, the richness. Sorry, it's just annoying. I'm looking at you, Edward. No, I'm just kidding. So we're all studying, no, right, so people are studying the math script. Why do it? Of course, it gives me it has applications to totally different kinds of things. We saw sort of one of them, but let me just give one of the reasons I like this. I mean, the first thing maybe I'll say at the same time is that it gives, you've heard the word characteristic classes of sigma G bundles are exactly, everything's going to be rational just for simplicity, are exactly elements of H star of the math class group, or H star, so keep switching around just for fun. And you see, the reason is just because what is a characteristic class of a bundle? It's just, it attaches to each bundle. Let me call this bundle psi. It attaches to it some number. Right? You just want to attach an invariant. So you give me an integer or a rational number. Well, we're big boys and girls. I think we're ready to look at cohomology classes. It's a generalization of numbers. Right? These dimensions of a vector, an element in a vector. So it's a cohomology class to every bundle, and you want it to be natural with respect to pullbacks. By which I mean, if I have a map from B prime to B, okay, smooth map from B prime to B, then I want to say, if I look at some this cohomology class attached to the pullback bundle, it's the pullback of the cohomology class. Now, if you have this, you just apply this every bundle. I didn't say this. I mean, B diff has this property. And maybe I'll skip instead of just B diff. Oh, it's slightly different. Crap. Okay, B diff sigma G has this bundle over it. It has a canonical surface bundle over it. It's the classifying space for surface bundles. So any surface bundle, as I said up there, it's just given by uniquely by a homotopy class of maps from B to B diff. So if you want things to be natural under pullback, everything just has to come from cohomology here, right? That's the usual game. Now you want to compute the cohomology. So that's one of the reasons I like it. But what I want to do is I want to tell a pretty simple story that goes from, I always love this because it's like, it goes from 3 fields metals and a direct, and I think actually deep connection from 3 fields metals to things that we all literally learned in first grade. And so it's great when math, I'm always saying to people, that thing we're doing now we call math, did you know that's the same thing we did like in high school? And it can be hard to, depending on which conference you attend, it can be hard to make that connection. And I would say, if you can't make any connection like that, then, you're too smart to be doing what you're doing. You should do something else. Some other topic in math. No, I'm sorry, it's just, out of control. Okay. Okay, great, sorry. So here's what I'm going to do. I'm going to convince you that the cohomology of MG is really like detecting things. It's interesting. And so I like doing this. I tell the story of 5 cocycles. In H2 of MG, or MG1 means with a base point. MG/MG star. Okay? Coming from like 5 different areas of mathematics. So the first one I actually want to talk a bit about, because this is sort of, Before I embark on this story, the second story I wanted to tell, which I'm guessing I'm not going to have time to do. Oh, actually, wait, it's an hour and 15-minute talks, but maybe I'll wait.
47 minutes.
Yes. It's what?
You have 47 minutes.
Okay. Great. Okay, so the first one I want to talk about sort of the order class on, and I hope that even, I definitely have, yeah, so there's a lot of points of view on this, and I'm not sure if, I think it's worth pointing out. On MG star is a moduli space of genus G curves with a marked point. And let me just say, so it's genus G curves with a marked point. We solved the fundamental group incarnation of this yesterday. You can forget that you've recorded a point and just record the complex structure on the surface. Then, of course, how many choices were there for the point? There's sigma G many. This is called the universal curve. Don't even start algebraic calculus. Complaining. Universal curve. And when you take fundamental group, you get the mapping class group homeomorphisms of a surface fixing a point up to homotopies that are fixing that point throughout the entire homotopy. You forget that you fix the point, and this subgroup is called the point pushing subgroup because here's an example, and it was Joan Berman who sort of, that's why Edward did the Berman exact sequence. Here's an element of the kernel here of pi 1 of sigma G. Oh no, it's sigma G. But here's sort of an element of the fiber. You could take the point and just, I'm on the same surface, I'm marking this point, this point, this point, and then you come back to where you started. So that's a loop. So pushing my finger, it gives me a homeomorphism of the surface fixing the point, but it's not, and it's homotopic to the identity, obviously. I just let go. If it's like rubber, I let go, and it brings back. But it moves the point. So if you don't move the point, for every loop, I get a, okay? Anyway, so, yes. So here's this bundle that I think probably everybody knows. And then this gives you an associated real two-plane bundle. We've seen it several times, the vertical bundle. Let's call this map pi. And we have the kernel of d pi is a two-plane bundle over, this is the vertical bundle. So what do I do? I'll just call it U. It's a bundle over mg star. Okay? Sorry. Yeah, it's a bundle over, two-plane bundle over mg star. Equivalently, you could look at equivalently.
So the kernel is a total space, right? Not U.
Oh, sorry.
The
No, the total space is.
This curve d pi.
Oh yeah, it depends what you call kernel d pi syntax. Yeah, thanks.
All right.
Neighbor. Equivalently, there's a complex line bundle over mg star, just given by the fiber at a point. I have a surface with a marked point, and I want the fiber at a point to be the tangent bundle at that point. And it's a one-dimensional complex vector space. So this is a complex line bundle. There's like 10 other ways to get this complex line bundle. It's the Hodge bundle. There's other ways. But by the way, there's an associated circle bundle here, right? When you have a two-plane bundle, you get a circle bundle. Just the unit vectors, you put a metric. Okay, so we're going to see that in a second. But you get this bundle, and so out of this you take the order class. I'm just going to call it E equals E of, let me call this bundle psi, every bundle psi. And it's sitting inside where? It's sitting inside H upper 2 of mg star. And I just want to remind you it's H upper 2 of like the mapping class group, of course. Sigma G star. Okay, any questions? So I just came up with one cohomology class. I want to say it's not trivial. How do you know it's not trivial? Yeah, I mean, you could give, and in fact, I think I'm running a book, but just like the circular order class. It's an infinitely rich topic. E is not 0, since, for example, so in terms of, how much do I want to say? Let me just say it this way. In terms of groups, at the group level, everything is a k by 1 here. So you have the mapping class group, sigma g1, map g1. The order class restricted when you take the Euler class and then you evaluate it actually on the surface, on the fiber, you get 2 minus 2g. There's going to be lots of other ways to see this very soon. Okay, but I want to talk more about the Euler class, because all the MMM classes come from it, everything comes from this Euler class, using the operations of taking powers and integrating over the fiber. And the kind of, I would say, a key thing that I would like to sort of communicate to algebraic geometers who maybe by this point probably know it, but I've met tons of people who don't know it. The way Nielsen tried to classify surface homeomorphisms, he tried to get the Thurston classification, and he almost got it. And in fact, Thurston and Handel in the 80s used Nielsen's idea to classify surface diffeos up to homotopy. It's very beautiful. Nielsen came up with an embedding of the mapping class group with a puncture embedded, and Thomas Caverda talked about this, into homeoclass of S1. And let me just be a little more slow. You have the hyperbolic plane, and this is genus G greater than or equal to 2. And by the way, let me just point out to you, this is false for the closed surface. For a closed surface, let me point out that you have finite subgroups that aren't cyclic, right? But every finite subgroup of homeo of the circle, exercise, every finite subgroup of orientation preserving homeos of the circle is cyclic. So you need that puncture, and we'll see why. And by the way, the reason you need the puncture, in fact, I just gave a proof, we'll see, I just gave a proof that the Euler class is not equal to 0. So his brilliant idea, Nielsen's brilliant idea is you start with a surface homeomorphism F, and you lift it to the universal cover. What you get is a quasi-isometry. And then, what's it called? Presaging Mostow. This was known to Morse. I found a paper of Morse in 1920, where you get a homeomorphism. You say, what happens to a geodesic? You hit it with the lift of F, and it goes to some crazy thing, but you show that thing always converges to a unique point. And then you show you get a homeomorphism of the circle. It's awesome, using hyperbolic geometry. Non-trivial theorem. So you get a homeomorphism, and let me point out, and why is that well defined? Because F is not a homeomorphism, it was only a homotopy class. I just made a choice. Well, if you make another choice, the two of us are homotopic. The two homeomorphisms are homotopic on a compact surface. So the homotopy, the point only moves, by compactness, a universally bounded distance in the hyperbolic metric. In the homotopy, any point moves, it goes 58. Distance 58, some fixed distance. And so the distance between F and G, the two homeomorphisms, is bounded. So then you show the basic hyperbolic geometry, they have the same boundary values in infinity. So he reduced the study of two-dimensional homeomorphisms of two-dimensional objects to homeomorphisms of one-dimensional objects. And then actually works, it's great. But anyway, for us today, why did I mention that? Well, I mentioned that because you look at this map, so this gives you a map from B mapping class group, which we've been looking at, to the classifying space for homeo plus of S1. Now there's this beautiful fact that you should prove yourself, at least for diff. This is an exercise for people here to do it for diff. This deformation retracts to SO2, right? SO2 is sitting in there, but it actually deformation retracts. It's super duper cool. Think about it for a second. You give me a diffeomorphism of the circle, I got to come up with a rotation in a canonical, super duper canonical way. Go. Okay? But so this is like BSO2, which is none other than CP infinity as a model. Now CP infinity, the cohomology of CP infinity, as you know, with Q coefficients, it's has one class given by a line, and that's the Euler class, it's the polynomial algebra. And that's the Euler class. And so you have the Euler class is sitting here. So E is in H2 of B homeo, S1. And you pull it back, you get the Euler class. The reason that you needed the puncture, that you needed to fix the base point, there were choices for lift of f. There are pi1 of the surface by any choices, right? The identity lifts to any deck transformation. And you might say, is there a coherent way? If you fix a point, here's a coherent way to lift. Ready? You fix this point. That means you preserve the lattice here. I just pick, here's a unique lift to pick. Pick the one that fixes that point. That gives you a well-defined map. Okay, questions? And in fact, you can't, this is not a subgroup of homeo, so you can't split this exact sequence. Because this has torsion, mod G has non-cyclic finite subgroups, and mod G1 does not, so this doesn't split. And that sort of gives you, non-zero Euler class. Let me give you a picture here with this one-dimensional kind of mathematics. Yeah, this is sort of one, I know I'm giving you 5 pictures, 5 2 co-cycles, and I'm still on the first co-cycle. Don't worry, the others are going to go pretty quickly. But this one is, I can't help myself, there's this story, and I get definitely, like I said, I want to transmit, because what I love about it is, it's sort of one-dimensional topology, and it has to have all these implications in algebraic geometry. And you'll still see. Great, so I just want to give sort of, that's where the Euler class is coming from. And another way to see it is that in terms of groups, take a homeomorphism. So if I look at homeo plus of S1, I can take the universal cover of that. That has S1 sitting inside of it. Fundamental group is Z. But in a less fancy way, I can take homeo of S1, twiddle, to be the set of all lifts of all elements. Right? Take homeo of the circle, I can lift it to a homeo of the line. In many ways. I take the set of all lifts, that is a group. That projects down to just homeo of the circle, homeo plus of the circle. And what are the choices for lifts? It's all the different translations. Right? So this is a central extension. Like the identity lifts to Z many things given by exactly the translation by multiples of 1. So this is what's called a central extension. Whenever you have a central extension of any group, it's given by, it gives you a 2 co-cycle. In fact, the extensions of this form, A goes to B with Z as kernel, are classified by elements of H2 of the quotient. So you get an element of H2. Giving the central extension, it's the Euler class again. That's an exercise. That's another way it comes up. And you can sort of see this guy is sitting inside homeo plus of the circle. And you see extensions are classified completely. Central extensions are classified by these elements. With the 0, the trivial extension, meaning the product, is the 0 class.
Why does that contain homeo plus the circle? You mean the real line?
No, it doesn't. Oh, this is inside homeo. Sorry, I meant to thank you. This is contained in. These are the periodic homeomorphisms. It's contained in homeo plus the real line. Homeo plus of the real line is torsion free. Right? Take any homeomorphism of the real line, it's orientation preserving. Pick any point, right? It's moving to the right. Keep moving, it's never going to come back. You iterate, it's never coming back. So, unless it's a fixed, everything's a fixed point. So it's a central extension. So because this has torsion, and this doesn't, this does not split, so the Euler class is not 0. I know that's not a big theorem there, but it's just good to remember these little things. Okay, so now I want to give my diagram. Okay. This is my diagram. Okay. And then I'll stop talking about the Euler class, as difficult as that is to do. I mean, for anybody who hasn't read Thurston's paper, though, on proof and progress in mathematics, like you should go and do it probably right now. It's more worthwhile than the talk. But he says that there are levels of understanding things, and he gives differentiation level 1, level 2, and he's like, here's level 37. And so this is my sort of excuse for concentrating on simple things. It's like, you can keep going. And I'm not saying I have level 37, but I'm trying to get to level n plus 1. I'm trying to get to positive numbers. So here's the diagram. So when you pick, well, let me give it without, look at homeo. Here's my global picture for the Euler class. Let me put it right in the center of the board. You have homeo plus of S1, and the Euler class is living here, in H2 of here. We just said that Nielsen shows, sorry, this contains, this contains, now let me give a diagram. This contains, this is an injection, the mapping class group with the puncture by the Nielsen's thing. Now, in order to do that, we picked a hyperbolic structure. We picked, like you have to pick a hyperbolic structure on your surface. I did that implicitly with this quasi-symmetry stuff. The mapping class group of a puncture contains pi1 of the surface, and this is that point punching subgroup. Any questions? On the other hand, and so you have the Euler classes living here, it restricts to the mapping class group, it restricts to the good old-fashioned Euler class here, which at the end of the day gives you 2 minus 2g by the Poincare-Hopf theorem, index theorem, right? You put a vector field, that's how you compute the Euler class. On the other hand, this group contains PSL2R is acting by real projective transformations on the circle infinity. And so this is sort of real projective, one-dimensional real projective geometry. But then you have hyperbolic geometry. Picking a hyperbolic structure gives a discrete, is the same exact thing as getting a conjugacy class of discrete faithful representations here. So you have this diagram, you have the Euler class here, otherwise known as the pullback of the area form. And this is a commutative diagram. And so you see the Euler class in all of its incarnations. Okay, the Euler class is classifying circle bundles over anything. But it's in the mapping class group, where's the circle bundle? Remember we had this complex line bundle? Where you put a metric on it so you have a unit tangent bundle? It's this circle bundle. It's some kind of universal circle infinity for hyperbolic structures. So I like this diagram, but I want to point out the following thing. And then we'll move on, I promise. PSL2R also has SO2 sitting in it. And we saw the Euler class here in the classifying space of SO2, right? The SO2 with CP infinity, right? Rotations. Inside here, we have Z mod 10Z, rotations by 2 pi over 10. You'll see why I'm picking 10. It's not special, but it's special to me and to you. Okay? So you have you can pull back the Euler class, restrict it, restrict it, restrict it. You get the Euler class, you get an Euler class in the second cohomology of Z mod 10Z. Let's say with Z coefficients. Or Q coefficients. Well, let's do Z coefficients.
You probably don't want Q coefficients.
Yeah, I don't want Q coefficients. Sorry, I don't want Q coefficients. Here I need Z coefficients. Sorry. Okay? So I need, what is a 2 cocycle on a finite group? It is a function. It is a function. It takes as input. I'm going to give you a function representing the Euler class. So I'll call it psi. Well, you have to input, what is an element of Z mod 10Z? It's a digit, 0 to 9, right? And you need to give me a cocycle. Okay? That's going to be not 0. And here's the cocycle. You can unravel the definition of Euler class. And you can absolutely, what I'm about to tell you, you can see it here. And therefore you can see it here. It tells you, it's called the carrying cocycle. I'll give you this. It's if A plus B is bigger than 9, sorry, it's 1, if A plus B is bigger than 9, and 0, if A plus B is, it's the tens digit. When you add 2 numbers, add 2 digits. And you can see, for people who know, I wish I could talk about the Milner-Wood inequality and all this stuff. You see everything. All that stuff is like obvious, you're just carrying. What you're measuring here is you're absolutely measuring, you're sort of carrying how much the circle is rotated. Anyway, I'm happy to talk to people later about it. By the way, and of course, the more familiar thing that people probably know, it's this thing, this multiplication by 10. Of course, 10 you can replace by any number. It's the 2 co-cycle. This is the central extension. So that's the element of H2 of Z mod 10Z. And that's the sequence. It's Z goes to Z by the times 10 map, and you take the quotient.
Are you concerned about the fact that the map from SO2 to PSO2R has a kernel?
Oh, there's a P too. Yes, I'm definitely not concerned about that this time. Yes, there's a P, there's SL2, I have to, right, sorry, there's little, right. I told a bunch of people, I think as an 80% correct mathematician, I'm like really pretty good. But as a mathematician, you know what I mean? Like, you can't pin me to be I'm really crappy, but as an 80%. Nothing's quite right.
I see.
No. And therefore I'm just saying, that's just, I'm sorry. So that was number 1, was the Euler class. That was only living in MG star. We definitely needed that star. Okay. Great. And let me just finish this story, and that'll probably be it. Then there's what's called the signature co-cycle. All the way back to MG. That's MG star, but here's the signature co-cycle. I'll call it sig. It's actually living in H2. I'm going to now go to MG. It's also an MG star. And the signature co-cycle, what is the signature co-cycle? It's supposed to eat, we have sort of the universal bundle. If psi equals the universal sigma G bundle. If you're wondering, that universal sigma G bundle and the universal curve, they're not quite the same thing because of this stupid torsion problem. In the finite cover, they're the same thing. The universal bundle, I always think of it as moduli space over Riemann surfaces with a marked one. See, it's basically 90% accurate. But anyway, if you take sigma's universal bundle, so what is the signature co-cycle? You give me what you're supposed to take a map of a surface. What is a 2 co-cycle? It's something that eats maps of surfaces into my space. I'll call it MG, it should be BDiff. But maps of a surface into my space, and it's supposed to spit out a number. So sig of f is supposed to give me a number, and I'm going to just define it to be the signature of the 4 manifold f star psi, which in other words you get, this gives you a bundle.
Do you really want a sigma G and MG, or should that...
Oh, sorry, sigma h, thank you. Sigma h. Or B, sorry. No, sigma h.
Yeah.
And then the base will be sigma h. So it's not obvious at all that that's a co-cycle, and that was proved by Meyer in like 1973. Okay, that's just another one that comes from 4 manifold topology. We have 1 manifold topology, 4 manifold topology. There is sort of a 3 manifold topology in my description. Let me give a few more co-cycles. Actually, could you tell me what time does it end?
Yes.
I can't do that computation.
7 past 12.
Okay. A third co-cycle you can come up with is that, well, like, MG is scalar. It's in fact a quasi-projective variety. So there exists a Kähler form. And this is what's called like the Weil-Petersen form, is the standard WP. And it gives you something in H2 of MG. Okay, it's the I'm going to switch to the reals. I have to multiply by like 1 over pi squared to get it to be rational, so I'm just going to, you're not going to bug me about that. Another one that sort of comes from, let me just say this, there's a map from MG. There's the oval Jacobian, there's a map that associates to a curve, it's Jacobian. So it's from MG, this is the moduli space of principally equalized abelian varieties. At the fundamental group level, which everything we're doing, homology and cohomology, at least with rational coefficients, mapping class group is the same thing as MG. So at the fundamental group level, by the way, this is just the usual map. The fundamental group of MG is the mapping class group, the orbifold fundamental group. And the orbifold fundamental group of AG is the symplectic group. So the Jacobian map induces this map. And to those of us who do low-dimensional topology, we're now feel good because this is just the axiom on H1 of the surface, nothing fancy. That's the induced map. But anyway, this symplectic group, you can look at the cohomology of SB2GZ because it's sitting inside SB2GR, and there's a whole story because you have the unitary group is sitting in there, and the deformation retracts to the unitary group. But at the end of the day, you have Turing classes here. So you have C1 in AG, or in symplectic group, which is actually, it's really beautiful. You can, it also is the Maslov index, which I guess I'll refer you to Andrew's latest book with
Jeez.
Geese. There's a story that's like actually richer than the one I just told that you can tell just about this one class. But anyway, you can look at Jack Star of C1. So let's see, okay? So there's another one. Great. And then finally, the MMM. There's the first MMM class. E1 is you can take E squared and then integrate over the fiber, or do the Giesen, anyway you want to do the Giesen map. And that has a rich story that we heard by Hannes. And this is in, so let's see, E2 is in H4, then you integrate over the fiber, so you get something in H2 of MG. Again, integrating over the fiber, my picture here is this picture, and that's the fiber I'm integrating over. Okay? In general, I can take e to the I and put an I here and put an I plus 2 here. Sorry, I plus 1 here. Okay, but here's different classes coming from different, sort of, lots of different parts of mathematics and very different parts. And that makes what I like about this, I guess what I'm trying to say is, well, let me give a theorem. Harrer for all G greater than or equal to 3, H2, I mean it's better than this, but just H2 of Mg, with, let me do real coefficients, is isomorphic, it's one-dimensional. So as a corollary, the signature is C1 times the Weil-Petersen class, and they're all proportional to each other, let me say it that way, by non-zero constants. All these parts of mathematics have to be the same, and you can compute the constants. And they're constants like the 4 that we saw. And so all these different beautiful things come into this picture. And it's Jack Star, C1, and it's so to me it's like I'm specializing all the way down just to the first time you have non-trivial cohomology. The first cohomology is 0 for MG. This is the first cohomology you see. The story I just told, and could go on telling for the next week, is just a discussion of H2 and how beautiful it is, and we could say so much more. And so if that one class, this is one class at the end of the day, everything here is one class, proportional, the rest must be amazing, and it's out there. But what I want to say is what is known, oh good, so I want to say the following thing. To end a little. Early, I'm not going to go a whole thing about what is known, but I'll say this. Maybe I just want to say one theorem. So the global picture, what is known, I shouldn't even call it a cartoon of what is known about H star of Mg Q. I know I said R here, I could just put a 1 over pi squared in front of something and then you can, so it's the same thing. And here's the cartoon picture for the rational cohomology. Just to condense time a little. What's called the virtual cohomological dimension of the mapping class group is 4G minus 5. That's Harrer. What that means is it's the supremum over all coefficients of the cohomology with coefficients in that module. So when Harrer proved in dimension 4G minus 5, when you prove that the module you're using ends up being some like infinitely generated abelian group. So then you can ask, in fact, Sam Brzezinski asked at some conference a while ago, how about rationally? It doesn't mean rationally. And so there was a Japanese team, but Andy Putman and Tom Church and I proved in the top dimension actually the cohomology is 0. So one open question
It's
is,
Morita, Suzuki, and Sakasa.
thank you, Morita, Suzuki, and Sakasa. And there's a whole story, Church, Putman, and I sort of conjecture vanishing here, but then there's this stable range, which is about 2/3 G. Oh no, sorry. Sorry, what do I say? I said, yeah, 2/3 G. And these are these MMM classes. I guess I won't talk about. They're all constructed from the Euler class, by the way, right? How is the Euler class and integrate? So we sort of know everything that's happening here. This is a good number of classes, but but there's this great theorem. I love ending with tension. There's a great theorem of, okay, come on, Harrer, stop taking everything good. It's easier to compute Euler characteristic than cohomology. It was not easy, the following theorem is not easy at all, but they amazingly managed to prove for all g greater than or equal to 3, the Euler characteristic of MG. Now it's an orbifold, so what you can just do is take a finite manifold cover and divide by the order of that group. So that's how we're defining it. It's equal to the zeta function of 1 minus 2g over 2 minus 2g. Oh, I have some other fun things here, but it's sort of like g to the g. So it's definitely greater than like 2 to... So you have super exponential growth. What does that mean? That means when you add up the dimensions of all the cohomology groups between 4g minus 5 and 2/3...
This is the orbifold Euler characteristic. It's not telling you anything about the cohomology there.
No, but it still does. It does have this as a consequence. You have to have a super exponential amount of, let me put this now, H star of mg. You have to have a super exponential amount of cohomology. There's only linearly many degrees you could have it in. The number of these classes, it's polynomial on each degree, and you're adding them up. That is sub 2 to the g. Or sub g to the g?
Isn't it going to be negative or something?
Ah, yes. And this is the, and in fact, in particular, sorry. And in fact, it's like minus 1 to the g plus 1. So it's negative half the time. So here's two disturbing things, not disturbing things. So these are the stable classes. And I claim the following. This was an accurate statement as of a few months ago, and it might have slightly changed because of Galatius and Coopers and Randall Williams and fourth person. Anyway, for g equal to 6, number of non-MMM classes. Here are these MMM classes. No, let me point out, what this says is two things. It says that the MMM classes are, this is 0.0000001% of the cohomology of mg, because we need a super exponential amount of stuff, and this is definitely less, this is most exponential. So we have encountered almost 0% with several hundred papers. They're very important. I'm not poo-pooing that, but I'm just saying. And even more disturbing, the MMM classes are all in even degrees. My deduction here is that if the Euler characteristic is super exponential, then of course you must have super exponential. Some beta numbers are super exponential. And here, in fact, you have sometimes this is negative. So you better have stuff in odd degrees. So the number of non-MMM classes and the number of classes in odd degree that are known for, they must exist. It's 0. So come up with an unstable class. It might be a small number now. I don't know, but I call this, and I'll end the talk on this, the dark matter problem. I just want to give it a catchy title. I think it's extremely compelling. And it's all out there, and every one of those super exponentially many things should have this story attached. So I'll stop. Thank you.
Thank you very much.
From which one?
didn't say.
But you only have to
Why?
relate them up with compatibility.
Either, so surface bundles in some sense is about the cohomology of diff, but as a topological. So discussing horizontal foliations means discussing the cohomology of diff as a discrete diff, which is quite different. So Morita's non-realizability comes from the fact that the MMM classes, indeed, starting with the third one, become trivial when pulled back to the diffeomorphism group as a discrete topology.
Yes.
So
I skipped that. You always have a map from, just to paraphrase, right? You have a map from diff with the discrete topology to diff with the continuous topology. You get a map the other way on cohomology. So Morita was really looking at this map in the MMM classes and this map, and this is for foliation.
So the pullback here kills the kappa I if I is at least 3. It doesn't kill kappa 1, and it's an open problem whether it kills kappa 2.
Which is the same thing as E2, what I'm calling E2. Up to a constant.
Okay, well, in that case, thank you very much.